This should be really, really interesting, actually. Yeah. So, all right, let's go ahead and get started. Take it away.
Amazing. Well, thanks so much for giving me the opportunity to talk about integrating AI and sustainability in modern architecture. I'm Sandeep Ahuja. I'm one of the co-founders and CEO here at Code Tool. We're an AI powered services company, and we work with projects across the country and in many parts of the world to make sure that they meet the local regulations as it relates to energy, carbon. They're able to be designed to be high performance and sustainable. This session aims to provide practical insights and actionable strategies that can elevate your project and align them with cutting edge technologies and sustainability goals. Here's just a quick note. And as I dive into kind of the core content, let's start by reviewing the key objectives. First off, we'll dig into what the different aspects of sustainability even mean, what the different types of analyses are. We'll talk about exploring embodied carbon. We'll talk about leveraging artificial intelligence. We'll talk about efficient methodologies for different teams and firms to start adopting some of this, or this doesn't need to be something out there for the larger firms or the firms with R&D budget, where this really is something that every firm can incorporate, and in fact something that can allow even smaller firms to be more competitive with the use of AI, which I think is really, really exciting. Just a little bit about me. I started my business about 7 years ago and have had the opportunity to serve over 60,000 projects since. I live, breathe, care entirely about reducing the global carbon emissions. This is the most recent book that I wrote that's published by Wiley. It's a textbook. It's called Build Like It's End of the World, because I believe that that's most definitely where we are as it relates to the building carbon impact. And this particular textbook, it really is about a journey to redefine the future of our built environment through the lens of decarbonization and introducing a new benchmark for sustainable design and construction. As we dig in, this is really, in my opinion, what it all comes down to. We might have all seen some version of this fact laid out in multiple presentations, perhaps in different conversations. But if you haven't heard it before, you heard it here. Buildings account for 40% of all carbon emissions and 76% of electricity consumption in the United States, which what that means as an architect myself in my previous life was a licensed professional designing buildings into the ground. And while I was while these buildings were getting built, of course, my goal and hope was that they would be around for forever and ever, right? Like for a very long time. And what I didn't know at the time was that how much carbon impact do they really have? A lot. If we care about, I don't know, if we have an EV or if we ride bikes or if we recycle or if we avoid taking plane rides, all of that matters. But in terms of the amount of impact that that can have, it's so much smaller. The entire airplane, the flight industry, that's like only 3% as compared to buildings, that's 40%. So all of us in this Zoom room together, we have an immense opportunity to make a massive impact by designing for efficiency and sustainability. And whether my original ask, of everyone on this call worked for you or not, whether you care about that or not, the point of the matter is that building energy codes are getting very, very stringent. And Florida is actually really also leading the chart. So as you can see in this particular graphic, it's the most recent graphic from 2024 of the various building codes across the country. And you can see that deep blue color right up top, which is the ASHRAE 90.1 2019, IECC 2021. That deep blue color is what Florida is in, and many states have adopted the most recent energy codes according to the 2020 State Energy Efficiency Scorecard. And while California currently exhibits the most stringent net zero building code, it's followed by several states in the Northeast, including Massachusetts, Vermont, Rhode Island, New York, and of course, Florida's in the mix. And so much of the code changes have to do with facade, everything from lowering the U value to reducing the window size. And since they are such major changes and there's so much to do with stringent solar heat gain coefficients or even limiting the amount of window to wall ratio, as we kind of read, if I put my architect hat on, as I read the code of the law, my architect side of the brain finds it far too restrictive. And when I read the energy requirements as a building material, wherein it's something that I can play with, something that I can explore. We really can come up with creative solutions while sticking with the budget, the client, the building occupant, gosh, and the world. So nothing easy. This is a very, very hard task that every architect is currently tackling. All of you are likely tackling. It's not an easy thing to design a building that meets all the regulations, meets everyone's requirements, and doing best by the world. So let's take a quick look at what that even means. So of course, the improved energy codes over in Florida, the 2021 IECC. There's some quick changes as I talk about the facade. The metal frame walls have stricter maximum U value improvements. Air barriers are now mandatory in most building types. New reflectance emittance ratings across slope roofs, penetration reduction, so on and so forth. All that I hear when I hear all that, or when I even say all that, is that, oh my gosh, more restrictions, more requirements. Wouldn't it be great if I could have floor to ceiling glass? My architect side of brain is so happy to have that floor to ceiling glass. Now, not that that is what you're after, or that is what I would like. I would love some great daylight, but what I'm after is holistic performance, not thinking just about energy, not thinking just about carbon, but thinking about great buildings, thinking about wonderful buildings that people want to be in. And that means having great daylight. That means having low glare. That means not having an enormous energy bill. That means making sure that our insurance quotes don't continue to get higher and higher because we've designed with that in mind. So let's talk about the key terminology. And that really comes down to total energy, embodied carbon, daylight, glare, and cost. So let's take a few minutes to dig into each and every one of those key terminologies. So when I talk about energy, and when most people talk about energy, that the metric that most folks are referring to is EUI, energy use intensity. You may have heard it before. It's been around for 10 plus years. That's not a new metric, but basically what all that it means is that if you're designing a particular building, let's say you're designing an office tower, if you average it across the entire office tower, the toilets, the places where people are sitting, the kitchen, the pantry, the data, the where all of the computers are hosted, and if you average it across the entire building floor plate, it's the amount of energy used per square foot over the course of the entire year. So typically that number is measured in kBTUs per square foot per year. And the lower, the better. And a lot of times you'll see the graph as it's listed here, where you can see how the building energy use breaks down for different types of usage, right? Like cooling and heating, of course, that's a lot. In this particular building type, there's a pretty high equipment load because perhaps it's maybe it's a data center. Maybe there's an abnormally high equipment load because they have a lot of equipment in there. I know in my previous life, I did a lot of lab buildings, very high equipment load, obviously. So this is a good way to kind of get a profile on your building, just like we have those nutrition labels behind the boxes when you're buying your chocolate, your candy, your food, your Coke, whatever it is. To me, this is like the nutrition label of the building itself to see how it breaks down, how high or low it is. So that's kind of a good way to think about it. Next up is the embodied carbon. Just as much the energy is important, so is embodied carbon. Now, energy is all about the energy used when you're operating the building, right? Like when I turn the lights on or when I turn my computer on. Embodied carbon, on the other hand, that is all about the carbon that goes into each material, each piece of glass, that carbon that goes into producing that piece of glass and transporting it to the site and putting it on the building. So it's the full carbon impact of your entire building, not just when I turn on the light, that's how much carbon it's going to consume, but taking it a significant step further to understand holistically how much impact is my building or my decisions making on the actual building. Just a little bit of an example I'll give you to think about how energy and embodied carbon can be quite different. So I was running a study for a K through 12 project here in Atlanta, which is where I'm based from. And in this K through 12 project, it was, like we were studying different types of glazing, double glazed and triple glazed. And there were 2 to 3 different types of double glaze we were studying and 2 to 3 different types of triple glaze we were studying. We were measuring which one we should use based on energy, so how much it reduced the energy use for the building, so EY. We were studying it against carbon. What was the total carbon that went into producing each of these glazing types? So the net carbon impact and the cost, right? That's always a very important parameter because I can never say cost is a constraint. Cost is the resource, and we always have to design stuff that fits into it to make sure our projects are real. So as I was studying these, 4 different options, 2 double glazed and 2 triple glazed options, the double glazed actually won. Not only was it lower embodied carbon, um, but it was lower cost. And the net benefit that I got from having double glazed versus triple glazed, because of course triple glazed will, make you use less HVAC. It just wasn't worth it. So we were able to go right ahead and make the double glazed choice versus the triple glazed. Um, and that was the better answer. So I'd encourage us all to kind of think about it in this multi-dimensional way. It's not one objective, it's all multi-objective. We're thinking about multiple things at the same time and balancing all of these different parameters. Next up is the spatial daylight autonomy, which of course is the daylight amount that goes into your building. This is the same metric that's used in LEED documentations as well. So if you're, going for LEED, you might have seen the SDA metric, being mentioned in that IQ credit. But it's a good way to see if your building is going to be well lit. For example, right now, the office that I'm in, well, it's a pretty gloomy, dark day with it raining outside. I will say that there is a very large window in here, and on most sunny days, I don't have to have the lights on because the lux level on my working plane, which is 30 inches above the floor, is high enough that I don't have to have electric lights on. And there's so many benefits of making sure that your building is naturally lit and well lit. Everything from uh, faster recovery times for hospitals to increased cognitive abilities in education centers and increased productivity in work setting. It's such direct relationship. And again, we can't improve and we can't incorporate what we cannot measure. So again, just putting it out there as we link into how we can start incorporating all of this into our actual design and practice. Um, Next up, of course, the annual solar exposure. It's really just a fancy metric tied to glare. So there's another story that comes to my mind. I was working on a renovation project. And in this renovation project, as we were kind of touring the facility, and I would encourage you the next time you're perhaps working on a renovation project, a restoration project, and you're touring the facility, if they have any blinds, watch the position of the blinds. Are the blinds, most of the blinds up, or are most of the blinds down? Now, in this project that I was touring, most of the blinds were down, which it told me 2 things. One, that human nature, we design all of these manual shades, but at least in a professional, non-residential setting, if these shades come down, rarely do folks make the effort to pull it back up. So human nature, always helpful, in all of that beautiful glass that was put behind it, meaningless, useless. All of the daylight that we hoped would come in, meaningless, useless, because the blinds were always down. 2, the most important thing that told me is that certain parts of the building had pretty high glare related challenges because the blinds were down, and most across every single individual office suite. So that's what you can analyze before the building is even built. That's what you can analyze on an existing project to even understand where the key challenges are so you can tackle it versus trying to apply these blinds across the board. Maybe you don't even need it in some areas and you can save that money and use it elsewhere in the project itself. So what you see in this graphic is kind of the 3D top view of the glare study. And green is good, yellow is okay, and red and deep red, that give me sunglasses inside kind of glare. So that's of course what we want to steer clear from and avoid, across the project. Now that we kind of have the basics down, I feel like we're talking the same language. I feel like we're able to use these words interchangeably, and I certainly will. Um, I want to go ahead and start talking a little bit about projects and case studies because that's such a great way of trying to understand how we can incorporate technology, how we can incorporate AI and bring that within our practice itself. So the first project that I brought with me is, again, I'm a little biased. I went to Georgia Tech, and I couldn't help myself but bring a case study from Georgia Tech because I had the opportunity as a sustainability consultant to work on the Georgia Tech Campus Center to renovate it. Now, just a little bit of context. All of these skinny, windows, the ribbon windows that you see up top, I mean, that did not do much. So I was typically the student sitting on the behind these ribbon or these not ribbon, these vertical slit windows and working on that little computer and hoping and wishing for more daylight. So when we were interviewing for this project and Georgia Tech was like, hey, we have this, existing building. It's roughly 100,000 square feet. We need to kind of redesign it to a 300,000 square foot building and expand it from the existing campus center and Tech Green and radiate it across the campus. That was such an exciting project. So the project itself, it stems from the original student center and it updates the 1970s building, which is what you see here. This was originally meant only for 7,000, faculty, staff, students. And now it's a campus to accommodate 23,000 students and 7,000 faculty and staff. So a significant change in the population size that was going to be utilizing this project, which meant the change in size. So this particular renovation now incorporates 3 buildings, the original one, in addition to an exhibition hall that's a separate and a pavilion, which is an additional cafe along a network of outdoor pathway and plazas. And the university really wanted to push the envelope literally and figuratively in terms of redefining the campus in terms of sustainability and performance. The integrated team with workshop architects, Cooper Carey architects, Newcomb and Boyd, and contractors, Gilbane. I had the honor to partner with them to really think through the stringent goals as it relates to sustainability, the stringent budget, because the 300,000 square foot project is roughly $100 million project too. So I'll let you all do the math on cost per square foot and what that means for what we were trying to accomplish and making sure that the aesthetic and all of the student bodies were appropriately represented. So as we went down this path, the first thing that folks wanted to understand was truly, well, what are we working with? What's our starting point? What is the current daylighting amount? So we ran the daylight analysis. Now there's a lot of opportunity to do so. We ran this particular analysis in the software that my company makes, and without trying to advertise it, market it, shamelessly plug it. The key reason that we used it is the key reason that most architects used it, as used by 70 of the top 100 architecture firms across the country, is because it's intuitive, it's fast, and we partner with you with our AI services to allow you to incorporate these studies much, much easier, really within days versus weeks. So what we learned here was that existing project was about a 16% SDA. It's not the best. 50% or so is the minimum LEED standard to even get the credit. Not that this project was going for LEED. But what you're seeing right here to break down how to even read a daylight map is we're currently looking at the plan view, and blue means no daylight, like almost never there is daylight over there. Yellow means there's some daylight, so it's got some good daylight quality. And orange means fantastic daylight. Like I wish I could just be in the space and it's going to be fully daylit. I may not have to turn my electric lights on most days, which is wonderful. But we had a good bit of ways to go. 16% is not a lot, and we were now getting ready to optimize it in terms of total energy, daylight glare cost, and of course, carbon. This is what we ended up with. As you can see, part of the building is still as it was, the part I'm annotating right here. This is the original building, and then this particular addition came on top of it, and we preserved, kind of that pathway with the Tech Green to make sure the students had the same point to go to that they were most used to. I'm gonna go ahead and remove these annotations clear my drawing. Wonderful. There we go. So what you'll see is also we kept those vertical split windows, but we introduced a lot more, windows along it. And what I can tell you is what I also want to showcase is all of these windows, how big they are, where they ought to be, what should we keep versus what we should get rid of, all of that. That is not guesswork. All of that is based on detailed studies. All of that is based on detailed analysis to make sure that we were optimizing, the total the glazing budget that have been set between the principal architect, the contractor, and the owner on the design build team. We basically had a fixed budget that no more glass in this because that would break the project budget. And I just thought that was such an interesting way to think about it and partner hand in hand with all around the table. The other thing that you'll note is that, again, while this was a design competition, in the competition itself, many teams presented idea that, it wasn't required to keep any part of this building. We could have entirely axed it, started from scratch, and not have to deal with anything existing or have to deal with any restoration. But truly, when we ran the embodied carbon study and we compared not just the embodied carbon, but the cost of renovating versus building from scratch, renovating was the better answer for reducing the embodied carbon, and it was the better answer for making sure we were optimizing the building budget. And I think that's what's so beautiful when we run the studies and we look at the analysis is how associated certain metrics are. It's not like what's good for carbon needs to be more expensive. In fact, in this case, and in many cases, what's good for carbon is also the lower cost option, so long as we're studying it. So as we were looking at this renovation, of course, you can see that we went from about 16% daylight to 36% daylight, which is a massive, massive improvement from where we were. And you can see kind of how the daylight is spread across the floor plate versus being just concentrated to one location. Of course, the depth of the floor plate was predefined because that was the historic depth. We didn't add any additional depth. And kind of in this new wing, which was added on, it's a little bit less deep than kind of this existing wing. So you can see that the daylight penetrates much, much deeper given the window to wall ratio and kind of how the windows were designed itself. Just as an overview, here's a section cut of the existing with the new addition project and the kind of strategies we looked at. We looked at everything from making sure we had high performance appliances to making sure we had sensors, all the way to making sure we had, glare control. We studied photovoltaic panels, although the budget did not allow for it. So at the end of the day, they never made onto the project, making sure the HVAC typologies were studied to pick the best type for lowest cost and highest performance, and of course, the glazing percentages. Here's the study that I find very, very fascinating. And we did it by facade, right? And just so you note, this particular study, as you can see, is for the south. And the next one you'll notice is for the east. I'm just highlighting this here so you can see kind of the differences by orientation too, because we really do need to understand the building, not just as a whole, but each component parts, because we can treat them differently. They don't need to all be uniform based on what is the optimal answer. So as we were designing the facade, the budget that was set for the south facade was really that 40% window to wall ratio. The south facade, again, for Georgia, Florida, kind of these similar locations, it's not that much different, is that south is pretty good. We can manage most of the glare by having some overhang, some shading. The west, now that is the hard one. East, we can still manage with some vertical fins. West is almost impossible to manage in our Georgia, Florida location based on the movement of the sun. Not that it's impossible to manage, it's just more expensive to manage because you have to put more fins. So we optimized the glazing on the south facade to make sure we could have daylight go in. But look at this. All four of these options, they all have the same amount of window to wall ratio. But look at this, the second one, and just how deep the daylight penetrates as compared to this one. The third one, the option 3 vertical slit. I mean, the daylight quality within these two spaces is so different, despite the fact that it's exactly the same glazing percentage. That to me is what I always find so fascinating and why we must always study how we want to design it, because it has such deep implications. The same thing for east. We had a 30% window to wall ratio budget on our east facade. And as you can see, kind of how that 30% varies from option 1 to option 3 to make sure that we could balance the daylight, the glare, and pick the best option. As you can see, option 2 really has the best daylight quality in terms of daylight and glare. And there's a 0% chance I would have guessed that. And I'd I'd challenge us all to think if there is any chance any of us could have guessed that. So if we've been guessing that, I'd encourage us to do differently. I'd encourage us to study these quick options. I'd encourage us to incorporate these opportunities within our design, incorporate some minor services like, gosh, this was maybe 5 hours of work, if that, if not less. And I think that's the exciting part, is the impact that it can make. Now, while we did incorporate a lot of early stage studies, as you can see marked up top, this was the concept and schematic design phase. We also did a lot of studying in this construction drawing phase, where we were truly doing VEs. And I think that's where also studies and data can be a really important tool in the architect's toolbox. So in this case, the pricing came back, and it was identified that some glazing needed to be cut. And while that was happening, what the team was able to do was truly find areas on the floor plate where cutting a little bit of glass would not cut a massive amount of daylight benefit. So you can see the before and after VE option, right? Like this giant piece of glass is converted to this kind of half glass and half just wall. And you can see down at the bottom the impact on the daylight. And while there is some impact, not that much. It penetrates just a few feet less, but there's still the daylight quality, the views are still there. And I think that's the exciting part. And we did the same thing here as well, where some amount of the glazing needed to be replaced with wall, again, purely from a VE standpoint. And the team was able to partner hand in hand with the contractors to figure out exactly where that ought to be, to have the least impact on the design quality and the least impact on the occupants of the building itself. Here we can see, kind of the same exercise. And yes, the same exercise again. I've brought a few different, you can see just the sheer level of detail, how something like this can be run on a room by room level to figure out exactly what needs to be preserved for the design integrity and what perhaps can be forsaken. Now, all of that I think is fantastic, because of course it helps our building be great. What I find most wonderful is the multi-objective optimization. And as you think about it, if each decision, right, let's say this decision is the decision for what type of glass, and then you study 2 different types of glass. And then within those 2 types, you study 2 different types of frames. You're kind of on a particular decision tree. You're not looking at all of the options. You're not looking at the holistic option, what it means to maybe, I don't know, use a very high performance glass, but perhaps that means I can use a low R value roof, and perhaps I have a very high performance HVAC, but that means that I can not add daylighting sensors. It's about that balance for the energy and the first cost of the project, not just the life cycle cost. And that's exactly what we did here. So we looked at the things that were on the table as an option: walls, different wall assemblies; roof, different roof assemblies; different window glazing options; different shading devices; photovoltaic panels; sensors, and set points. So as you can see right here, for roof, we had the option of having our 25 roof, our 30, our 35, 40, 45, and next to it, you can see the cost per square foot for each of those options. We did the same exercise for different glazing types, right? Like different cost per square feet. Different wall assemblies are 13, 19, 24. again, with the cost per square foot and the PV, the sensors, the shade, and the HVAC system. And of course, this project was going for the performance path in terms of the energy code regulations. So we really had a little bit of flexibility to play around and figure out the best way to kind of make it happen. Now, that's a lot of options. Let's kind of take a look at what this means. And yes, I will acknowledge it. This is a daunting looking graph, but let me break it down and it will make a lot of sense in just a second. So each vertical axis here is the decision point, right? Like roof R value, these are the options we just looked at. Skylight U value, glazing type, each is an option, right, that we just looked at. And each blue line is one possible option, is one possible alternative in the mix. And we were looking at cost premium, so the money that we would have to add up top, payback years, and what that meant in terms of energy savings. So key things that were important to this particular client, and whatever that means for your clients and for your project, those parameters can change accordingly. So then we worked with the design team hand in hand to use these sliders, because anything over a 10-year payback was a no-go. The owner was like, if it's more than 10 years, do not even show it to me. And of course, in this case, this is an institutional owner. It's higher ed. They're going to own this building for a long time. So I can see why their payback year tolerance would be higher than many others. If you're working with a developer, maybe the payback tolerance is 2 years. And that's okay too. We can just bring the slider down to reflect what that means for your owners. And the energy savings possibility we were able to see right here. And then further, if we really want to define the lowest EY, the lowest energy use intensity for that payback years, we found this option. By investing only a total of $79,000 extra, we could get 8% energy savings with a 5.4-year payback and a 60 EY, which is just exciting for us to be able to do, and was most definitely what was helpful for this particular project. I have a few more things that I wanted to talk about in terms of yet another case study, but I'll pause there for a second, give you all another opportunity to type in all of your questions in the Q&A tab, and we'll keep on going because I will address all of the questions at the end. So definitely keep populating those. Amazing. Let's keep on going. So high level, if I think about the case study that we just talked about, the key things that were unique about this particular team were, one, their embracing of technology and open-mindedness for all options on the table. Two, their pursuit of design excellence and making sure that the building was holistically performing well, not just from an aesthetic standpoint or not just from a programmatic standpoint, but truly holistic building performance was high. And three, their embracing of data beyond all doubts. They were willing to not assume anything and truly follow the data where it took them. And in this case, the data took them to a renovation versus a new construction, which most definitely was something the owner was open to, but the design team pushed for a renovation because that was the better answer for this project. Now let's study a mixed use office and residential project. In this case, totally different building type, right? Here it is. It's fully built now, and it's a tower. It's new construction, no renovation, not low rise, entirely different in every way. Here's kind of the plan view, right, of the site. You can see right here, kind of it's marked, right? You can see the site right there. It sits kind of in this dense urban environment, and you can understand this is roughly a 667, 667, gosh, yeah, 1,000 square foot office tower. and it really grows to the, more office space. It's mixed use. It has retail, hotel, multifamily. It's got a little bit of it all. It truly is a mixed use project of the future. And of course, because this was a new construction, the very first thing that we were able to do hand in hand with the design team was try to get a better understanding of the climate. Now, things like climate studies to understand the yearly temperature, solar radiation, humidity, temperature, etc. All of this can be done firsthand by AI-powered tools. Vitros AI is another AI-powered tool that allows you to just type in your project location and your project type, and it can produce a quick benchmarking report for you. It can produce a quick weather analysis for you, and it's completely free of cost for everyone to use or sign up, no matter where you are. So it's a great way for teams to start incorporating and truly understanding the climate profile of the location that you're designing in. Now, if you're designing where you live, you probably understand the climate profile pretty well. But if you're doing projects outside of the location that you're most comfortable with, this is a really, really, really great place to start getting a sense of what it is that you're looking at. Where's the solar radiation even coming from? Where should you, what this, for example, tells me is that where should I likely make sure that I have I don't know, a pool deck if I do have a pool deck? Or where should I think about having the least amount of glass because it's going to be hit with really hot summer sun and drive my HVAC loads up and make me size my HVAC bigger, which I don't want to do. So that's the kind of insight you can get very, very, very early on. Or in this case, in terms of the wind study, to be able to understand pretty quickly where the wind direction is coming from in terms of summer and spring, where I want the wind, where I want to optimize for that and cater for that. And of course, the passive strategies, there is something that can even work and what the adaptive comfort looks like. The other analysis that is super critical, the study that we do again and again and again in every project that we consult on, is the shadow study, especially for a building in a dense urban environment. Maybe a lot less relevant if your project is in, kind of a big open piece of land because, well, there's not much that will come in the way of it except the project itself. But here, this project is in a dense urban environment, and we really needed to understand how the shadows played a role, what part of the facade would even be fully exposed versus what part of it would be in shadow. So maybe it's not worth it to put a lot of glass there because we wouldn't get any daylight because it would be covered with the shadow of the neighboring project. The kinds of things one needs to think about. What the radiation looks like on the vertical elevation of your project. What does it look like? Where is the sun going to be the hottest? So we ran a microclimate study in this case because it gets really warm. And again, I have nothing to say to anyone joining from Florida, with this being the AIA Florida session from a climate zone standpoint. Y'all understand heat better than I do here in Georgia. Although I am ethnically from India, so I have some sense of what heat is. But y'all understand heat, and being able to understand the microclimates that are created in these hot, humid settings is super critical. Perhaps what does shade do? So, for example, what we were able to understand was that a part of a exposed patio, exposed porch outside where we wanted folks to enjoy being outdoors, if it's shaded, it was 10-degree cooler than if it was fully exposed. And that can vary by project to project. It will vary location to location, but that's super insightful information. So if we wanted, perhaps we were designing a pool deck and we wanted some areas to cool down, there's ways to think about, not just pool umbrellas, but where the architecture itself could lend itself to creating these pockets of microclimate across the project. And of course, benchmarking is so critical to understand, how do buildings of this typology typically perform? How do I compare? Just like I talked about the nutrition label, right? Like behind each thing that we consume, food, drink, right? There's that nutrition label. This is 80 calories. This is 180 calories. But until I know what my calorie budget is, I guess that information is fairly meaningless, right? Because I guess I would go up to 2,000, 3,000 if I didn't know perhaps the budget was 1,500, and that's what the benchmarking is so critical for, to be able to set a baseline on how this project type with this climate zone compares to projects of other types. Am I better than average? Am I worse than average? Am I right at average? And it really helps us benchmark ourselves as well. Of course, as any Class A office, daylighting was a very key component of it, where we were studying kind of making sure that daylight penetrated deep into the building floor plate. And as you can see, on floor 26 or floor 10 or floor 14, there was 46 to 76% daylight. It's absolutely phenomenal. And some of these floor 6, as you can see right here, they have perforated metal on top of it, but that's really parking deck. So the fact that it only has 21% daylight, it's okay. It's a parking deck. The cars will be fine. We really were optimizing for daylight for the actual office space where the occupants were going to be. Next, we were also trying to optimize for the facade, right? Like studying different types of shades, everything from horizontal fins to vertical fins to gridding, to really understand how we could remove all of the glare in this office tower. And then, of course, finally trying to understand the total photovoltaic impact, right? Like as you can see in the first option right here, that's it. That's all the PV panels that there is. In option 2, there's a little bit more. In option 3, there's a little bit more. And you can see exactly the impact that they all have in terms of reducing the overall energy use intensity of the project. And I think being able to look at these options was very critical for the developer owner in this case to be able to understand how far they wanted to push the envelope. And again, even with such sustainability minded owners, it always has to make economic sense, because if we're not bringing things back to the economic sense or the local energy regulations, it really begs to question why we're doing what we're doing. I'll tell you about a story similar. It was an office tower in Tampa that I had the opportunity to work on. I don't know, maybe it was about 6 years ago. And the code was, of course, a lot less stringent then. It had, one of those famous architects, which I shall not name, but ones that have an office in pretty much every city. And in this particular Tampa office tower, what we realized after we ran the studies with the owner as well, was that the cheapest way, the actual lowest cost way to get to code compliance was to put photovoltaic panels, because they were adamant about having the floor to ceiling glass. That was a mandatory aesthetic. That was a mandatory ask for the developer to be able to attract the rent, et cetera, that they wanted to attract. And truly, the way to do it was to add a little bit of photovoltaic panels on the roof, and that brought the energy use intensity down enough that the building was able to meet its local energy code, which I thought was so fascinating when we did the performance-based path and applied for the compliance of that particular project. And that's really how I think technology can be such a close and tight-knit partner of project teams, to make sure that it's not something that's on the side, it's not something that's added on top, it's not something that's done at the end. It truly is an integrated partner of the design team, so that we can continue to push the envelope forward and continue to really make a massive impact in what's truly possible in terms of the project itself. I did want to use this opportunity to share an open offer for all that are joining this particular webinar. It's a complimentary, let me reshare my screen just right here. So it's a complimentary offer open to all of the members of AIA Florida in particular. So I'm hoping you can see my screen now. This is a link that I'll add to the chat window as well. Is a free project consultation. So for y'all, if you're working on a particular project that comes to mind, whether it's, even in pursuit stage, concept, pre-design, schematic, design development, or gosh, if you're just looking for, you're right at code compliance and you just want to have a second set of eyes, you can click on this link and schedule yourself a free project consultation. And our experts in sustainability and our experts in consulting will be in touch with you and will be happy to provide more insight as it relates to how you can optimize your project and how you can think about ways to make it even better. With that, I will go ahead and open it up for questions. So if you haven't already popped one in yet, please definitely feel free to do so now.
Do you
So
see?
the first question,
Do you
go
see
for
the
it.
one starting with Donna?
I certainly do.
Okay.
Amazing. So one of the questions that came in is how do you calculate the ASC? So what the AS with the ASC, what happens when the neighbor building changes its light pollution, which affects another buildings, and who is responsible? It's a great question. So the basically, if I had to put it in plain terms, what I think you're asking is, what happens to your glare if perhaps, someone puts a giant reflective building next to your project. Unfortunately, you can't predict future, and no models can predict future. So there's not much you can do then. But I will say, an example that comes to mind, I don't know if y'all have heard of the walkie-talkie tower in England, where it was so reflective that folks were literally making eggs in skillet next to it. And of course, then they had to remedy it. Of course, if someone does that in the past, you can make sure that you have appropriately designed glazing and appropriately designed facade for your project. But if it happens in the future, perhaps the only way to remedy that is either by adding some external or internal shades after the fact. So long as it's code compliant for the other building to do what it's doing, there's not a whole lot else I think you can do. I hope that answered your question. Amazing. The next question that I see is, can you speak about incorporation of circadian rhythms into the lighting considerations? I mean, most definitely, circadian rhythms are a lot more associated to, kind of the electrical lighting and how the internal lights and the electrical lights, the day lighting, the electrical lights come together to make sure that the environment is wonderful. But there's most definitely sensors that you can design that change the lighting temperature and illuminance across the day to make sure that, the circadian rhythms are matched. You might even have seen in some airlines, if you're taking it in an international flight, many times the light temperature that comes on, depending on the color and temperature that comes on, depending on the time of day that you're taking the flight, is designed in the way that, your circadian rhythms are taken care of and are soothed. But that's more of a design feature of electrical lighting fixtures and lighting fixture design than the day lighting itself. Hopefully that answered your question. Another question that came up was from Patrick. Well, thank you for saying this is a great presentation. Thank you for that. What is the target payback years in terms you're seeing with most owners understanding each project and demands are unique? What trends are you seeing in the next 5 years? I will say that the target payback years really varies building type to building type. And as you would imagine, depending on the ownership expectation within that particular group, because again, if the intention of building a project is to perhaps immediately sell it, then the tolerance in terms of payback is typically under 5 years. However, I have seen owners that are holding on to the asset for a longer period of time. Under 10 years is typically considered pretty pretty standard, pretty average. Under 5 years is considered great. So I'd just say that targeting, under 5 to 10 years is probably the right benchmark. But again, each owner, depending on their, future plans for that asset type, will have the biggest impact. Well, it looks like I might have answered all of the questions. Happy to stay on for another minute or so to see in case you might have any additional questions, but definitely would would be happy to answer it. It's been an honor to present to you all, to answer your questions, and to share with you all a little something about the things that I care so deeply about and the things that can have such a deep impact on our practice and something that we can all impact together.